We're going a bit further with permutations, people, and we are looking at indistinguishable objects, where objects of the same type are indistinguishable. All right. So sometimes we do treat them as treat them as indistinguishable, some objects or elements. Okay. So let's go straight into a couple of examples, because I have another video on this, and this one is a supporting video for it. And we'll look at a simple example first up. So you can see ball and ball. Okay, so what have we got here? Versus. Well, if we look along here, B-A-L-L, with no distinguishing features between the L's, alright, is treated differently to a situation where we have L sub 1 and L sub 2. So we'll demarcate that with two different colors. Okay, and so the pink color for distinguishable, and for indistinguishable the blue color, or turquoise. Along each of the rows we can see different arrangements of the letters. Okay, so let's look at row 1. So for the first part we've got one of the arrangements could be A, B, L, L. Now if we look at the distinguishable arrangements, we've got A, B, L, L, but we have to put in sub 1 and sub 2. There'll be another version of that arrangement with, well, I guess it's not another version, there is another separate arrangement, I should say, more accurately, if we put 2 than 1. Okay, so for all these others, alright, and there's 12, you can try this yourself, with a simple table, but a direct reasoning. For B-A-L-L, where L and L are indistinguishable, there'll be 12 different arrangements there. Okay. Well, for distinguishable, we've got, for each of these, we've got, we can have in every case we can have from left to right L1 before L2, or the vice versa of that. Okay, so you have 1, 2, 2, 1, 1, 2, 2, 1, and so on. Rightio, and if you did that in a very long-winded approach using a table, and I'm not advocating that because that's why we're learning these bits of maths here, more efficient, but nevertheless you would get 24, which would be correct, 24 such arrangements. So in essence we see that for each of these rows, which are for each arrangement in B-A-L-L, indistinguishable, we get 2 different arrangements for distinguishable. So there are twice, in this case, there are twice as many arrangements if we have distinguishable versus indistinguishable. So in other words, we have half as many if it's indistinguishable. So in terms of permutations, we can say the following. So the number of permutations of the L1, L2 pair. Now, by the way, that's 2 factorial from our previous work, or pretty easy directly to see that. It's 2, isn't it? You can have L1 then L2 later, or L2 then L1 later. Okay. If we have that times the number of permutations by direct reasoning of ball indistinguishable, and we found out above that that's 12, we get the number of permutations on the right hand side, the 24. Okay, B-A-L-L, where L1 and L2 are distinguishable. Now we also saw that with direct reasoning above, that it was 2 times 12, which is 24. Or we can see that it's 4 factorial because we have 4 distinct objects, and that's a permutation. Alright, so 4 factorial is 4 by 3, which is 12, by 2 is 24, by 1, which is 24. Okay, so all we need to do now is rearrange this, you see, and we've got what we need. So for the number of permutations in BALL indistinguishable will equal the number of permutations for BALL distinguishable over the L1 number of permutations for L1, L2 as a pair. Okay, which we've got all those numbers, and so for this particular case, if we started with the distinguishable case, you've got 24 on the numerator there, or 4 factorial, same thing. Okay, over 2 factorial. Now that's in essence the application we're looking at in this video. Let's extend and generalize on this, but extend first by a slightly more complex example and then generalize at the end of our video. We've got Pepper with the letters indistinguishable on the left versus Pepper with the P and the E as separate distinguishable elements or objects. You can see the subscripts there. So a good question to frame for this is, for this Pepper here, how many arrangements are there if we consider basically, as I said at the start of the video, objects of the same type are generally considered indistinguishable. Okay, so many of the questions will be framed around that. So how do we find all the arrangements or all the permutations for Pepper given that the P's and the E's are indistinguishable? Okay, alright, so it's just an extension on the previous word ball. Okay, except we have one more factor to consider as well. Now for Pepper distinguishable, we've got 6 characters, 6 indistinguishable or unique characters, and that would have 6 factorial arrangements possible for it. Okay, so we've got that there, but we've also got, if we looked at the if we kept the P's all static but we changed the E's around, that would generate 2 factorial arrangements. Okay, and you could try this if you want to pause the video and create a little list, but you could also look at if you kept the E's static and looked at all of the arrangements for the P elements there. So if you kept the E's and the R, I should say, I forgot about R that's sitting on the end. Okay, if you kept all those 3 letters static and moved the P's around, you would generate 3 factorial arrangements, okay, which is 6, right? And 2 factorial, of course, is 2. Okay, just keep that in mind. So if we were to do a table like we did above for ball, we would know that this Pepper with indistinguishable characters would generate fewer arrangements possible than the distinguishable version. So we need to multiply the number of permutations or arrangements for Pepper indistinguishable by a certain number to get this one on the right. And by doing a table, and I'm not going to do that, you could do that yourself, it'd be a bigger table this time, you would see that the all of the variations on P1, P2, P3, E1 and E2 would create 2 factorial by 3 factorial, and we multiply that in a similar way as we did above with ball by the number of arrangements in Pepper indistinguishable. Okay, so we get that. Alright, and if you did do the table, bearing in mind that factorial 2 times factorial 3 is 12, you get for every arrangement for Pepper, you'd get 12 of the corresponding arrangements for Pepper sub 1, sub 2, sub 3. Okay, the distinguishable one. That's why I didn't do the table, and it's a good advertisement for learning some advanced maths techniques, because that would be a mongrel of a thing to have to create in that manner. So this is a better way. So the number of arrangements possible for Pepper indistinguishable, or number of permutations for it, is just a rearrangement of the line above as we did before. So it's a number of permutations for 6 objects basically, because they're distinguishable. Getting sick of writing pepper. Okay, and I better get that right, hold on. Okay, I didn't put my subscripts in there for P and E. And rearrangement means it gets divided by 2 factorial by 3 factorial. Okay, and so that's pretty much it. So let's generalize that, or actually we could actually come up with an answer that would be a little bit more satisfactory than just leaving it as a sort of a formula there. So if we're trying to find the number of arrangements in pepper where they're indistinguishable, we can work out, we'll easily evaluate the bottom, so that's 12, alright, and the top is basically 6 factorial, isn't it? Okay, so very easy to work out. So that's 60 arrangements. Okay, so to conclude, in general, if we have n objects in total, we have n sub 1 objects of the first type, that might be the letter E, okay, n sub 2 of the second type, that might be the letter P, and so forth. Okay, you get words like Woolloomooloo or Mississippi and things like that, they have several of these. Okay, but there's also other questions. It's not just about letters. Okay, my other video shows a bit of that. There's plenty of examples around where this is used not just with letters in words, and it goes up to n sub r of the final element of, you know, which we tend to consider. We don't worry about all the ones that there's just one of, because they all have 1 factorial arrangements, which is just 1. So you can see that in the formula on the bottom, if we divide them by 1, it makes no difference. So that the R type really is the final repeating element, okay, in the case of indistinguishables. So if we have all these things, and strictly speaking, it is all of the separate types of objects in there. Okay, but as I said, in a practical sense, we can just look at the repeating ones only. But strictly, it's n1 plus n2 plus the everything up to the last one should be the total. Alright, so yeah, strictly that's true, but in practicality you don't need to worry about it because it's 1 factorial for those single entities. So given that, then that means there are n over n factorial, I should say, over n1 factorial times n2 factorial by all of them up to the final one, nr factorial. Okay, and there'll be that many. Now linear arrangements, more about that in a future video. That's an optional word, because some arrangements actually are circular and they're done differently. So if you haven't seen that yet, don't worry, that's a word coming your way. But linear, the important thing, arrangements, okay, of the given n objects. Okay, so that's the number of ways of arranging the given objects. So now you have a way of dealing with indistinguishable objects, and it's just basically modifying the n factorial. Okay, so hopefully that helps a bit, and I do have a second video on this.